we're going to get started. First of all, I'm just going to jump into the Canvas course for just a moment to show some things that I've added, hopefully to make the course a little bit better. Yeah, hopefully, we'll see. But yeah, wow, no one wants to be here this morning. It's crazy. Got like half the class missing. Interesting. All right. Oop. Got no. All right, so here is the class. Hopefully you can see my screen. Hopefully you're familiar with this now. If we look at our calendar here, we're all the way almost to the end of January, right? We're on the 28th. We'll get the recording in here later. If you would like to see all the slides from today ahead of time, or if you wanted to, you could have there right here in the calendar already. There's that. Looking forward to February. I don't have anything loaded up in there yet, but do take note that starting next week. No worries, Nathaniel. Starting next week, the weekly T lesson is with period 2 all month. So you'll have 3 Mondays in February. That will be with period 2. That's me. So you'll see me first thing in the morning on Monday mornings for the T lesson. Right, so please remember that. Other than that, we have a pretty standard month. We will miss a meeting day in February, right? President's Day, there will be no school. So there'll be only one day that I see you on this week in February. Similar to what happened with your 135 classes this week, where you only got to see that class, those classes once, right? Just as a reminder. Also, if we look in our modules, the things you might need, I've added a link down here, including we have our formula sheet and tables, right? That includes your table A, formulas that will be provided to you when you take the AP exam, those types of things. If you click on this how to use table A, this is a couple of videos I made last semester, just demonstrating how to use like z-scores and table A, going forward and backward, going from the inside of the table out or the outside of the table in. All right, so hopefully that is helpful if you need that review or if you want that review. There's also a lot of things on YouTube and such if you want to check those out. Also, Khan Academy has a whole section that's AP stats that follows along pretty closely to the course of our textbook. With very similar topics and things like that. So that's another resource if you'd like to check that out. I'm not going to add it to the Canvas page because I feel like if I add too much, it's just going to be overwhelming. All right. Also, in our Chapter 6 module, right, I've added this right here. This is a video I recorded over on Tuesday. Right? I worked on it on Tuesday. It took a while because it is me working out 5 different problems. They're all free response questions that involve using all parts of Chapter 6, right? With our random variables, transforming and combining random variables, binomial and geometric random variables, all those things, using table A and such. All those things happen in this video with different problems. So this is meant to be kind of like a review of the types of problems you should be able to solve with what we've done in Chapter 6. I do have this set up. So, well, it's supposed to have chapters. I might have to update this video link. I set it up to have chapters so that you can find the problems easier, but apparently that didn't come into this link because I linked it earlier. I'll reset that. Either way, that'll be a thing. So there is that as another resource for you to review before you do the assessments. All right. You should be after today, right? And possibly after doing some examples tomorrow in class, you should be ready to take the assessments for Chapter 6. They are both said to be due on the 29th, which is tomorrow. That is just because I wanted their due date to be before we start Chapter 7, which we start Chapter 7 next week. Please keep in mind, those are just guidelines for pacing so that you know that this assignment came before another assignment and it came after others. And you do not lose credit for turning it in late. I don't penalize if you turn it in next week or the week after or whatever. Take the time you need to do this well. But I would recommend kind of working on it over the course of the next week, right? So because this is when chapter 6 will be most fresh, all right? Are there any questions about the course or the assessments? Alrighty, so then please get some note stuff ready. We're gonna have some new stuff to do today with chapter 6. We're gonna be jumping into section 6.3, which is the last section of chapter 6. So if you've got a notebook, if you've got a piece of paper, if you've got something you take notes on, which you should, now's the time to have that ready, as there will be some things you may want to put in your notes. Right? So with that, we're going to get started. Section 6.3 is on binomial and geometric random variables. All right, we've been talking with random variables. We've done discrete and continuous. This is continuing along with those lines. So here we go. So in this lesson, we're going to learn how to determine whether the conditions for using a binomial random variable are met. Right, there's special conditions that we must consider. We're going to compute and interpret probabilities involving binomial distributions. We're going to calculate the mean and standard deviation of a binomial random variable and interpret these values in context. We're going to find probabilities involving geometric random variables. And we're going to see when it is reasonable or appropriate to use the normal approximation to the binomial distribution to calculate probabilities. Noting that this last thing is not necessarily required for the AP Stats exam. However, do keep in mind anything in the book is fair game for AP Stats exam. Just because they said it's not required doesn't mean a part of it might not show up. All right. So these are the things we're going to look at today. We're going to see some examples of some of these things, but not all of them. But we will see some examples of them tomorrow when we do our practice problems. So what is a binomial setting? So when the same chance process is repeated several times, we are often interested in whether a particular outcome does or doesn't happen on each repetition. Right. Some random variables count the number of times the outcome of interest occurs in a fixed number of repetitions. Right. This is kind of the important thing here. There's a fixed number of repetitions. Previously, we've just given a random variable, and there's maybe not necessarily a fixed amount of things happening, but there's a fixed possible number of outcomes, right? So now we're doing a fixed number of trials or repetitions. When we have that, we have a binomial random variable. Binomial setting arises when we perform several independent trials of the same chance process and record the number of times that a particular outcome occurs. The 4 conditions for a binomial setting are the following. These you'll want to write down. Is it binary? Right. The possible outcomes of each trial can be classified as a success or failure. Right. Is it independent? Right. Trials must be independent. That is, knowing the result of one trial must not tell us anything about the result of any other trial. Right. Consider like flipping a coin, right? Every time you flip a coin, those are independent trials. Knowing that the first time you flipped it, it was a heads, tells us nothing about whether or not you'll get a heads on the second flip. Those are independent. Right. Number. Right. The number of trials n of the chance process must be fixed in advance. All right. So maybe we're doing a coin flipping thing, and X is recording the number of heads, and each trial, or my trials I have is like 5 flips of the coin and I record how many heads. Maybe I do that a bunch of times, right? And I want to have X record how many heads I have from 0 to 4. Right? That's fixed. I'm only flipping the coin 4 times and recording. Success. There is the same probability P of success on each trial. Right? Again, this ties into independence, right? Pretty much the only way that we can have the same probability of success on each trial is if those trials are independent, right? That is part of the reason why we have this independence condition. Right? And to remember these things, we use the first letters of these binary independent number and success, and remember that we must check our bins. Right? If I want to know if something is binomial, or if I can represent it with a binomial distribution or use a binomial random variable, I have to check the bins. So that's kind of nifty, an easy way to remember. All right. Can you please raise your hand if you need a moment to write any of this down for your notes? All right. So consider tossing a coin n times. Each toss gives either heads or tails. Knowing the outcome of one toss does not change the probability of an outcome of any other toss. If we define heads as a success, then P is the probability of a head and is 0.5 on any toss. The number of heads in n tosses is a binomial random variable x. The probability distribution of x is called a binomial distribution. Right, so the count x of successes in a binomial setting is a binomial random variable. The probability distribution of x is a binomial distribution with parameters n and p. Right, where n is the number of trials of the chance process and p is the probability of a success on any one trial. Possible values of x are the whole numbers from 0 to n. Okay, so this still has a lot of the same characteristics as the random variables we've seen over the course of this chapter, right? The random variable represents the number of times something occurs. In this case, we're considering it the number of times a success occurs in a set number of trials. So there's that set number that sets it apart from our other random variables that we've considered so far. Can you please raise your hand if you need time to write anything down? So in a binomial setting, we can define a random variable, say x, as the number of successes in n independent trials. We're interested in finding the probability distribution of x. Right, so we have our example here. Each child of a particular pair of parents has probability 0.25 of having type O blood. Genetics says that children receive genes from each of their parents independently. If these parents have 5 children, the count x of children with type O blood is a binomial random variable with n equals 5 trials and probability 0.25 of a success on each trial. Right? In this setting, a child with type O blood is a success, S, and a child with another blood type is a failure, F. It's important to understand that when we're using probability lingo and statistics, success and failure doesn't have a positive or negative connotation to it or implication. It is just success is the thing that I'm tracking, failure is the other stuff that I'm not tracking. Right, what is the probability of having exactly 2 children, right, with blood type O? That's what the probability of x equaling 2 represents. So one possible way to have 2 children with blood type O is if the first 2 kids are both type O and the other 3, the last 3, are not. Right? Since these are independent, right, and it's a kind of a succession of things happening, we can think of this as possibly like a tree diagram like we've seen previously of we have a kid, they either have type O or not, right? These are independent. And after that kid, there's another kid, so on and so forth. We could build a tree from that. These are and connections, so we multiply the probabilities. right? Probability of having the first kid blood type O and the second kid blood type O, and the third kid not, fourth kid not, fifth kid not. We multiply these together, we get 0.25 squared times 0.75 cubed, and we get 0.02637, about 2.6%. However, there are a number of different arrangements in which 2 out of the 5 children have type O blood. This is only one of 10 possibilities. Finding the probability of one of these possibilities is not the answer. We need to find the probability of any one of these 10 possibilities occurring. Right? That increases the odds. Right? We can verify that in each arrangement, we end up with the same multiplication of 0.25 squared times 0.75 cubed. And this has to do with properties of multiplication. No matter what way I multiply things, 2 times 2 times 5 times 5 is the same as 2 times 5 times 2 times 5. Right? The order in which I multiply things together doesn't change the outcome. Right? So we end up with the same probability for all 10 scenarios. So that means that the probability of x equaling 2, having exactly 2 kids with type O blood, is 10 times the probability of one of these scenarios occurring, which is 0.2637, about 26%. Is there any questions on this process so far? All right. And does anyone need a moment to write anything down? Okay. So note, in the previous example, any one arrangement of 2 S's and 3 F's had the same probability. This is true because no matter what arrangement, we multiply together 0.25 twice and 0.75 3 times. We can generalize this for any setting in which we are interested in K successes in N trials. That is, the probability of X equaling K is equal to P of exactly K successes in N trials, which is equal to the number of arrangements times probability of success to the K successes power times the probability of failure, or 1 minus the probability of success, to the power of the number of failures. Right, so the power for successes is the number of successes. The power for failures is the number of failures. And we multiply these things by the total number of arrangements or number of possible outcomes. All right, the number of ways of arranging K successes among N observations is given by the binomial coefficient. That's what this is. All right, and we read this as N choose K. Right? And we stack the letters up here in a tall parentheses. There is nothing between them, just air, N choose K. And this is equal to N factorial divided by K factorial times N minus K factorial. Yes, in math, we've given a meaning to the exclamation mark because we thought it was so much fun in English. All right, so for K equaling 0, 1, 2, all the way up through N, where N factorial, it's a very excited N, equals N times N minus 1 times N minus 2 times 3 times 2 times 1. And remember, 0 factorial is equal to 1. You can check it in your calculator. This is a property of factorials. We do not have time to cover why this is true in this class. It's outside the scope of our class, but know that it's a thing. All right. So essentially, N factorial says multiply the number N by all the numbers that preceded it until you get to 1. So like 5 factorial will be 5 times 4 times 3 times 2 times 1. Right? 3 factorial is 3 times 2 times 1. Right? So it's a notation that allows us to say all of this multiplication in a single like number with exclamation mark, which is kind of nice. And your calculator can do this for you if you want. Your calculator can also calculate N choose K. So I'll show you that real quick. where to find this on your graphing calculator if you have the school issued graphing calculator. Otherwise, if you have a different type of calculator, you'll have to kind of look this up and figure out where it is, because I have no idea what calculators you guys have. Anyhow, to find the n choose k command, right, what you'll do is say we wanted to 5 choose k, which was what we did in the previous problem. 5 trials, 2 successes, right? We have 5, and then we'll go to math, right under alpha. Click over till we're highlighted on probability, PRB. And then the third option here, NCR, is N choose R. We'll click on that, and we'll say 2 after that. So this is saying 5 choose 2. And we see that there's 10 possible ways to have 2 successes in 5 trials. All right, we could change this up, and maybe we're interested in 6 choose 3. Right, so there's 20 possible ways to have 3 successes in 6 trials, right? These numbers get really big really fast if we keep going, right? So that's how you can have your calculator do that calculation for you. You can also use this calculation in parentheses along with other things if you need to. So that is an option. And I do believe we have factorial in here. I'm not entirely sure where it is, though. I did not look for it yesterday. All right, so that's good news. We can have this calculation done, which we will need for the next thing. This formula, the binomial probability formula. The binomial coefficient counts the number of different ways in which k successes can be arranged among n trials. The binomial probability, P of x equals k, is the count multiplied by the probability of any one specific arrangement of the k successes. Right? If x has a binomial distribution with n trials and probability p of success on each trial, the possible values of x are 0, 1, 2, up through n. If k is any one of these values, then we get the formula. Probability of x equaling k is equal to n choose k times probability of success to the power of k successes times the probability of failure to the power of number of failures. Okay. And again, this is number of arrangements of k successes in n trials. This is our probability of k successes, this thing here. And this is the probability of n minus k failures. So this is our binomial probability formula. Right. And I'll show you how to do this in your calculator on the next thing, because that's always convenient. Does anyone need a moment to write this down for their notes? Alrighty. So then we have some steps that we can take to find binomial probabilities. Step 1, state the distribution and the values of interest. Specify a binomial distribution with the number of trials n, success probability p, and values of the variable clearly identified. Right, so in our previous example, that would be saying with the blood type O, there will be n equals 5 trials. We have a probability of success of 0.25, and the random variable x can have values 0, 1, 2, 3, 4, or 5. Okay, and we could show this with the probability distribution or like a histogram or a table if we wanted to. That would be one way of really demonstrating possibilities. Right. Step 2, perform calculations. Please show your work. Do one of the following. Use the binomial probability formula to find the desired probability. Do it by hand, calculate all the numbers, do all that fun stuff. Or we can use the binom PDF or binom CDF command and label each of the inputs. All right, I will explain what this is momentarily. All right, last step of this thing is answer the question. Make sure you're doing all this work and then answering the question that was asked, right? If you're asked, find the probability of having 2 kids with blood type O and interpret the result in context, finding the answer is only part of answering the question. You must also interpret the result, saying what it means, right? Don't forget those parts. So now, what does all this represent here? So we have 2 separate functions going on here, or commands that we can use in our calculator. The binom PDF command, right? And we use this command if I want to know an exact value, right? So if I want to know the probability of x equaling k, right? The binom CDF command is used if I want to know the probability of x being less than or equal to a value of k, right? So if I want to know the probability of exactly having 2 children out of 5 that have blood type O, we use binom PDF. If I want to know the probability of having 2 or fewer kids with type O blood, I use binom CDF. Right? So they each have a specific use. Right? When it says to label each of the inputs, we have 3 inputs for this command. Right? We need to have the number of trials, that's one input. We have the probability of success, and what's the value of k that we're interested in, right? The number of successes. These 3 values will be used in both of these commands, right? And so if you're using this to answer a question and like you're showing your work, you say, hey, I used the binom PDF function in my calculator to calculate this result. You'll have to write out like binom PDF, parentheses. Sorry, sometimes my tablet thing here freaks out and gets input from somewhere crazy, right? So we have n equaling, for our example here, 5, p equals 0.25, and k equals 2. All right. You need to show it in this way so that it's demonstrating that you understand the parameters that must be used and what they're representing. Right? It's not enough just to say I use binom PDF. You need to label the inputs. Right, so now on your calculator, to find these, you go to second and then hit the button that says vars. Right above it, it says distr, distribution, right? And we get this list of things. This is also where you find the normal PDF, normal CDF. Right? There's some other distributions we'll talk about later, a Poisson distribution. Right? We're going to look at option A and B here, binom PDF and binom CDF. If I want binom PDF, going along with the example we've already seen with the kids and type O blood, hit enter, and it will prompt you for the inputs. Right? Number of trials, 5. Right? What's the probability of success? 0.25. X value, they use X instead of K in this case. That's just, I think, easier for the calculator. We want 2. Right, so the X value is 2. It goes along with our K value that we're interested in. We'll then hit down to paste, hit enter, and hit enter again. Lo and behold, we get the same exact answer that we were supposed to get. The 0.26367, a bunch of decimals, right? About 26%. Right, so the calculator is set up so that it can run this calculation for you quite easily as long as you have the correct parameters. All right. So yeah, and we can do the same thing. It asks for the same three numbers if we're doing binom CDF. You just need to know that the CDF one does less than or equal to. Is there any questions on these commands in your calculator? Or anything we've covered so far? Okay. Soon we will move on. Does anyone need a moment to write anything down from this slide? Okay. So we'll look at a couple examples. Right. Each child of a particular pair of parents has probability 0.25 having blood type O. Suppose the parents have 5 kids, so it's the same context we've seen before. Find the probability of that exactly 3 of the children have type O blood. Right? We'll let X again be the number of children with type O blood. Right? We're giving the details that we're going to use. Right? We know X has a binomial distribution of N equals 5 and P equaling 0.25. So probability of X equaling 3 is 5 choose 3 times 0.25 cubed times 0.75 squared, which is equal to 10 times 0.25 cubed times 0.75 squared, and we get 0.08789, about just shy of 9%. All right. This question only said find the probability. It did not say to interpret or explain what this means in context, so we're done. Question B, should the parents be surprised if more than 3 of their children have type O blood? Right. To answer this, we need to find P of X being greater than 3. We do not have a command in the calculator for greater than, so please keep that in mind. Right. Probability of X being greater than 3 is the probability of X being 4 or 5, right? So we have P of X plus 4 plus P of X equaling 5. Again, this is the OR condition, right? When we have an OR condition and they are independent events, we just add those probabilities. This goes back to stuff we saw in previous chapters, right? So this is equal to 5 choose 4, all this, 5 choose 5, we get all this. Notice we have a 0 for an exponent here. Anything to the power of 0 is equal to 1, right? 1 million to the 0 power is 1. All right, please remember that. It is not equal to 0, it's just 1. All right, and ultimately we get 0.01563. We found this probability, however, we have not answered the question. The blue box here shows the answer to the question. Since there is only a 1.5% chance that more than 3 children out of 5 would have blood type O, the parents should be surprised, right? That's really slim odds. Right, now we've answered the question. Right, this result here is not the answer to the question. It is the evidence we need to answer the question. Any questions on these two examples?
I do.
Yes.
How did you get 10 next to the probability of X equals 3?
This one right here?
Yeah.
That is what 5 choose 3 is equal to. Right, so if we do 5 choose 3, that's equal to 10. So there's 10 ways to have 3 successes out of 5 trials. Because there's 10 ways, I multiply the probability of having one of those successes, which is 0.25 cubed, 0.75 squared, times 10. And that's what this represents here. Does that answer your question, or would you like a different example?
It does. Thank you.
Okay. Excellent, excellent. Any other questions? Or anything else I can clarify? Thank you, Maria. That was a good question. All right. So now let's move on to mean and standard deviation of a binomial distribution. I recommend for this slide, if you are taking notes, you don't necessarily need to write down stuff from this slide. It's the slide after this that has stuff you should write down. This is going to go back to things that we've already seen. So we describe the probability distribution of a binomial random variable just like any other distribution by looking at the shape, center, and spread. All right, we're going to consider the probability distribution of X, the number of children with type O blood in a family with 5 kids. Right, we have our histogram and our table showing that probability distribution. The shape, right? Probability distribution of X is skewed to the right. It is more likely to have 0, 1, or 2 children with type O blood than a larger value. It's just interpreting the histogram. Center, the median number of children with type O blood is 1. That would be the median. Based on our formula for the mean, we get this craziness, right? The mean of X is equal to the sum of the probability of each outcome times its probability, right? And that's what this calculation shows here. And we get 1.25. Spread, the variance of X, right? And again, this is the same calculation and same formula we used for random variables, right? Any random variable, right? The outcome minus the mean squared times probability of that outcome. We do that for each of our 6 outcomes, and we get 0.9375. That leads us to a standard deviation of 0.968. So these here are calculations that we've seen previously. It's the same way that we would calculate mean and standard deviation for any other random variable. Luckily, this is a binomial random variable, right? We've already said that. We have a shortcut for calculating mean and standard deviation that doesn't take nearly as much work and saves lots of time. Right? If account X has a binomial distribution with number of trials n and probability of success p, the mean and standard deviation of X are, mean is n times p, right? So number of trials times probability of success, and standard deviation is the square root of n times p times 1 minus p. In other words, the square root of the number of trials times probability of success times the probability of failure. Right? And that gives us the standard deviation. That also infers that this under the square root sign is the variance. So if you're ever asked for the variance, you can easily calculate that as well. Right. Please note, these formulas work only for binomial distributions. They can't be used for other distributions. All right, so if the random variable in the scenario does not pass bins, it's not a binomial distribution, you cannot use these calculations. You have to treat it as just a typical discrete or continuous random variable. Right. So we need a moment to write these down for your notes. Okay. So next we'll see an example of finding the mean and standard deviation. Here we have Mr. Billard's 21 AP Stats students did an activity in our textbook about telling the difference between types of water from like tap water and bottled water. If we assume that the students in his class cannot tell tap water from bottled water, so they're purely guessing, then each has a 1 in 3 chance of correctly identifying the different type of water being by guessing. Let X equal the number of students who correctly identify the cup containing the different type of water. Right. So in here, right, we could check that this passes our bins test, right? It's binary. They either guess right or they guess wrong. Right? It is independent. One kid guessing right has no impact on the next kid guessing right, as long as the experiment's set up properly, right? There's a specific number of trials, 21, and the probability of success is consistent for each trial, right? There's a 1 in 3 chance of success. So this passes bins, so we know it's a binomial distribution. All right, so we're going to find the mean and standard deviation of x using our new formulas. Since x is a binomial random variable with parameters n equals 21 and p equals 1/3, we can use the formulas for the mean and standard deviation of a binomial random variable. Very good. So the mean of x, or the expected number of students who would correctly guess the water, is n times p, or 21 times 1/3, or 7. All right, so we'd expect about 1/3 of his 21 students, about 7, to guess correctly. Okay. Standard deviation, we have the square root of n times p times 1 minus p. That gives us the square root of 21 times 1/3 times 2/3, and that's 2.16. So if the activity were repeated many times with groups of 21 students who are just guessing, the number of correct identifications would differ from 7 by an average of 2.16. So again, these are much, much easier to use than our other types of calculations for mean and standard deviation of random variables. So it is nice that they are here. Is there anything I can clarify about this example? And does anyone need a moment to write anything down from this example? All right, binomial distributions in statistical sampling. The binomial distributions are important in statistics when we wish to make inferences about the proportion P of success in a population. Almost all real-world sampling, such as taking an SRS or simple random sample from a population of interest, is done without replacement. However, sampling without replacement leads to a violation of the independence condition. All right? That could be a problem, right? We need independence to use binomial distributions. Right. When the population is much larger than the sample, a count of success in an SRS of size n has approximately binomial distribution, with n equal to the sample size and p equal to the proportion of success in the population. Right. This is good news. Right. This leads us to our 10% condition. Right. So if we're checking bins, right, and we're dealing with something that we know is a simple random sample of a certain population, and using a binomial distribution is easier than not using it, we can check the 10% condition to satisfy the need for independence. Right? So when taking an SRS of size n from a population of size capital N, we can use a binomial distribution to model the count of successes in the sample as long as little n is less than or equal to 1/10 big N, which means the size of our sample is less than or equal to 10% of the entire population that we're sampling. Right? As long as we can satisfy this condition, I can use a binomial approximation and a binomial distribution, which again can be much easier than just treating this as a random variable, just a normal random variable. Right? Is there any questions on this condition? Does anyone need a moment to write it down? So then, normal approximations for binomial distributions. Okay, this is the category of thing that may not be on the AP exam, so we're just going to briefly talk about it. As n gets larger, something interesting happens to the shape of a binomial distribution. The figures below show histograms of binomial distributions for different values of n and p. What are we going to notice? Here's our first one. We have 10 as our n, 0.8 for p. Next one, n is 20, p is 0.8. Right, so the number of trials is increasing, and the shape is looking increasingly normal. We go up to 50 trials, and this looks almost like a nice, perfect, normal curve. Right, so as we do more trials, this distribution looks more normal. That's also good news because we have a whole set of things we can use with normal distributions that make it easier to calculate probabilities. Okay. So the normal approximation for binomial distributions, otherwise known as the large count conditions or large count condition. Right, suppose that X has the binomial distribution with n trials of and success probability P. When n is large, the distribution of X is approximately normal with mean and standard deviation calculated the same way we did previously. The mean is n times P, standard deviation is the square root of n times P times 1 minus P. Right, so the mean and standard deviation are calculated as this is a binomial distribution. As a rule of thumb, we will use the normal approximation when n is so large that n times p is greater than or equal to 10, and n times 1 minus p is greater than or equal to 10. That is, the expected number of successes and failures are both at least 10. If this condition is met, that means I can use a normal approximation to calculate probabilities, which can be helpful, especially if I'm dealing with large numbers, right? That could be very good. We're not going to see an example of this today, but there is, I believe, examples of this in the problems that I worked out. Does anyone need a moment to write any of this down for their notes? So next we get into geometric settings. In a binomial setting, the number of trials n is fixed and the binomial random variable x counts the number of successes. In other situations, the goal is to repeat a chance behavior until a success occurs. Right? These situations are called geometric settings. Right? A geometric setting arises when we perform independent trials of the same chance process and record the number of trials it takes to get one success. On each trial, the probability P of success must be the same. All right, so the difference between this and a binomial setting is that this doesn't have a fixed number of trials, but we have an end point when I get my first success. Okay, so if you're being asked to find something, to find like what's the expected number of trials before the first success, that falls into this geometric setting, as long as the probability of success is the same for each trial. Right? We have that condition of independence that still needs to exist. Does anyone need a moment to write this down? So in a geometric setting, if we define the random variable y to be the number of trials needed to get the first success, then y is called a geometric random variable. The probability distribution of y is called a geometric distribution. The number of trials y that it takes to get a success in a geometric setting is a geometric random variable. The probability distribution of y is a geometric distribution with parameter p, the probability of success on any trial. Possible values of y are 1, 2, 3, and so on and so on and so on. There's technically no end point for the possible values. It could go up through 100, 1,000, 2,000, right? It depends on what's going on. We can't necessarily rule out any large value at this point. Like binomial random variables, it is important to be able to distinguish situations in which the geometric distribution does and doesn't apply. Once again, the main thing we're looking for is, are we being asked to determine when we hit our first success? If we see that type of thing, then most likely it'll be just a geometric distribution that we can use. Okay, so let's look at an example. In this example, we're going to consider the lucky day game. Right? We have not seen this context, so I'll give you a brief rundown on the context. In this game, all right, a teacher plans to give 10 homework problems to his or her class. As an alternative, the class can agree to play the lucky day game. Right? A student will be selected at random from the class and asked to pick a day of the week. right? So they have 7 options, Monday through Sunday. Then your teacher will use technology to randomly choose a day of the week as the lucky day. If the student has picked the correct day, the class will only have one homework problem. If the student picked the wrong day, then the teacher will select another random student who will then choose another day of the week, and the teacher will then randomly choose another lucky day. If the guess is correct, then the class will have 2 homework problems. Right? The game continues until a student correctly guesses the lucky day. The teacher will assign a number of homework problems that is equal to the total number of guesses made by members in the class. So that's our context here. All right, we're going to have the random variable of interest in this game is y, which equals the number of guesses it takes to correctly match the lucky day. We want to calculate what is the probability the first student guesses correctly, the second, the third, what's the probability the kth student guesses correctly. Okay. We use this kth for the general rule. So the probability of y equaling 1 is 1 over 7. Right? There's a 1 in 7 chance that the student guesses correctly. Probability of the second student guessing correct, which means the first student was incorrect, is 6/7 times 1/7. And again, this here is the probability of being incorrect times probability of getting it correct, 0.1224. Probability of y equaling 3, right, which means the third student was correct, implying that the first 2 were incorrect, means we have 6/7 times 6/7 times 1/7. We have probability of wrong times probability of wrong times probability of correct. Okay, so that's how these are being built up, right? Because then again, this is measuring how many times it takes to get first success, right? This yields us a formula, right? If y has the geometric distribution with probability p of success on each trial, the possible values of y are 1, 2, 3, and so on. If k is any one of these values, then the probability of y equaling k is equal to 1 minus p to the power of k minus 1 times p. Again, 1 minus p is the probability of failure times the number of failures, or not times, to the power of number of failures, I apologize, times probability of success. Probability of success will always have the power of 1. It will only be multiplied by once. Is there anything I can clarify about this example or the formula? And does anyone need a moment to write this down? So then we can have the distribution here. The table below shows part of the probability distribution of y. We can't show the entire distribution because the number of trials it takes to get the first success could be an incredibly large number. Right. So we have our histogram and the table. Giving me to describe shape and center and spread. The shape, this is a heavily right-skewed shape, and it is characteristic of any geometric distribution. It's because most likely value is 1. That has the highest probability, is the first person getting it correct. Center, the mean of y is 7. Right? We'd expect it to take 7 guesses to get our first success. Kind of makes sense. There's 7 things to choose from. We would think like, well, it should take maybe at least 7 people to get one correct answer. All right, our spread, the standard deviation of y is 6.48. We will not get into this calculation today. If the class played the Lucky Day game many times, the number of homework problems the students receive would differ from 7 by an average of 6.48. It's kind of a big swing. So the calculation for the mean or expected value of a geometric random variable is given here. If y is a geometric random variable with probability p of success on each trial, then its mean or expected value is 1 divided by p. Right. Pretty straightforward. 1 divided by the probability of success. Right? In this example, 1 divided by 1/7 is 7. Right? So if we have a geometric random variable, calculating the mean is pretty straightforward. Right? 1 over p. Right? Is there anything I can clarify on this example or this calculation? All right. And lastly, we have the ability to ask our calculator to calculate probabilities based on geometric distributions. To do this, we use the Geomet PDF or Geomet CDF calculations. They work the same way as the Binom PDF and Binom CDF. Right? The Geomet PDF, right? Option E here calculates the probability of y being equal to a specific value of k. Geomet CDF calculates the probability of y being less than or equal to a specific value of k. All right. This command only asks for 2 parameters, right, or 2 conditions, the probability of success and the x value or value of k that we're interested in. All right. And so we could do the same thing. We have I want 1/7, right? And what's the chances that it takes 5 guesses? Right, so the probability of it taking 5 students to get the first correct answer would be about 7.7%. Right. So we do have the option of using the calculator to calculate these probabilities using the Geomet PDF or Geomet CDF commands. Right. And with that, we have reached the conclusion of the presentation. All right. We did all the things we said we were going to do at the beginning, which is fantastic. So there we go. All right. Is there anything I can clarify? Is there anything you'd like to go back to in the presentation? All right. So before I let you guys go, please keep in mind we've now completed chapter 6. Tomorrow in class we will look at some example problems, kind of like what we did last week. I've created a Desmos activity for us to do problems on. Hopefully that is useful. Other than that, I definitely recommend looking at the practice problems for 6.3 in Canvas, seeing if you can make sense of the problems and seeing if you can work through some of the problems. And if you have questions, please let me know so I can help you and help increase your understanding of the content. Other than that, if you have any other questions about today's lesson or previous lessons or previous work that we've done, please let me know. You're welcome to stick around on this call to ask for support or help if you'd like. Other than that, we are done for today, and I will see you guys tomorrow morning for more practice with section 6.3. And that's it. Have an excellent day, and I'll see you tomorrow.